Swayam Prabha. Digital India. Educated India.
So welcome back, and so I hope you got some time to discuss about the question that we left unanswered. So are there examples where the algorithm does not terminate? So recall that we have an n cross n bipartite graph. We have preferences of A's and B's. We have defined what is a good matching, which is a stable matching, and we have also given an algorithm which starts with all the men being or A's being unmatched and repeatedly lets an A which is unmatched to propose to the most preferred B that he has not yet proposed to. And this keeps on happening as long as there is an unmatched A. Now the question is, will this algorithm terminate or in finite amount of time, or will it cycle and keep going on forever? So there were two camps. One said that it will always terminate. One said that it may not terminate on examples. So is there an example where it doesn't terminate? Okay, so if you have failed to find out an example, then there must be a reason why we have failed to find out an example that on which it doesn't terminate, if you have tried, right? So let's get back to the way the algorithm executes on any general instance. So recall that we have started executing the algorithm from the A side, that is the A's keep making the proposals and they go in an order, right? So we would like to ask if we can say that the total number of proposals that happen throughout the course of the algorithm is bounded by a particular number, then we will ensure that the algorithm terminates, right? So let's ask, how many proposals can a particular A make? What is the total number of proposals? At most n, because his preference list is of length n. At some point he may stop because, for example, if A1 had got assigned to B4, he never had to propose anybody beyond it. So the other thing is that once an A has made a proposal to B, he doesn't make a proposal to the same B again, right? Therefore, in its preference list, it goes from left to right, and it makes at most one proposal to every to a woman or to a B, and the total number of women in his preference list is exactly n. The total number of proposals that a particular man makes is bounded by n, and this is true for every man, right? Therefore, if you have n men, each of them will make at most n proposals. Therefore, after n squared proposals, the algorithm is guaranteed to terminate, right? We have only shown a very basic property that the algorithm does terminate, and it terminates in time which is proportional to the number of proposals that is made by the algorithm, but the number of proposals that is made is at most the number of edges in the underlying bipartite graph, which is upper bounded by n squared. Therefore, the total number of and once you make a proposal with some amount of bookkeeping, you can quickly answer whether that proposal is going to get rejected, or you are going to be in this case where you change this matching to remove the old edge and add a new edge, right? So this is all work which is constant time. I am assuming that you have done some amount of asymptotic notation. So therefore, this algorithm takes time which is proportional to order n squared, where n squared is the number of edges in the graph. So therefore, it is in fact a linear time algorithm, because this is actually equal to order m plus n, right? So this is, in fact, m is exactly equal to n squared, so I can leave out this, but this is the running time of the algorithm. Okay, so what we would like to show is that this algorithm indeed outputs what is our desired matching, which was what was a stable matching. So we would like to show that this algorithm once it outputs a matching, it will be a matching which is stable or which does not have any blocking pair. This is what we want to show. But before we go and prove that, we would like to point out one particular thing about this algorithm. So there is this sentence, while there is an unmatched A belonging to A, right? So to begin with, there are all A's which are unmatched, and very conveniently in our algorithm we picked up some order A1, A2, A3, A4 just by their naming order. Is there a particular order that this algorithm needs to follow? Is something that is a question that we should ask, because think of it that if you are coding this algorithm, you would want to tell your program that okay, if you maintain it as a stack, it is going to pick it up in one order. If you maintain that unmatched men in a queue, it is going to pick it up in another order. If you have to always sort it according to their names A1, A2, then it is going to pick it in that order and so on. So does it matter if the order of this algorithm is changed? So we'll do a quick run of this algorithm with a different order. So what we did is, we are just going to do the same thing, that is the A's propose and B's reject based on the proposals that they get. So we'll run this algorithm, instead of A1, A2, A3, A4, we'll just run it as A4, A3, A2, A1, right? There's no need to do this, but one fixed order. So we will let A4 propose to B4, it gets accepted. A3 propose to B2, it gets accepted. A2 propose to B3, it gets accepted. A1 propose to B2, what should happen at this place? There is a conflict because B2 has two proposals now. So B2 evaluates between A1 and A3 and it rejects the proposal of A1, right? And now A1 goes and proposes to B4, and at this moment again there is a conflict because B4 is currently assigned to A4. So B4 evaluates between A4 and A1 and it rejects A4, and now A4 is free and therefore A4 applies to B1, and at this place the algorithm stops, right? So if you look at what are the partners, A3 still gets B2, A2 still gets B3, A1 still gets B4 and A4 still gets B1, right? So this, and since it is the same matching, there is nothing to verify. Indeed it is a stable matching, we have already verified that. But what this example at least illustrates is that irrespective of this order, we got the same matching. This again may or may not be true in general. The example may be a contrived example to illustrate this. So we would like to ask such questions, because otherwise every execution may give us a different assignment depending on how you execute that algorithm, right? Okay, again before we show that it is stable, is there any other way of executing this algorithm apart from of course all possible permutations of A's? Is there any other way? What do you mean by B as consideration? Okay, so her suggestion is that we have somehow given preference to A, and we are, so while this instance is very symmetric, there is an n cross n bipartite graph, each A has a preference over B, each B has a preference over A. We have still now introduced a symmetry in our algorithm by saying that the A's propose and B's reject or accept based on their preference, right? So now it is conceivable to ask, can I run this algorithm by letting the B's propose and A's assume the role of accepting or rejecting? So let's do that. So let's say B1 will do the same thing, it's just the roles of A's and B's have changed. So B1 proposes to A2, B2 proposes to A4, B3 proposes to A1, B4 proposes to A2, and there is a conflict now. So now it is the role of A2 to decide based on the preference of A2. So A2 looks at its preference and sees that B1 is better preferred than B4, therefore it is going to reject this, and B4 continues. B4 proposes to A1. Now there is again a conflict. Yes, you have a question? Okay. So A1 looks at the preference, and between B3 and B4 it finds that it is B4 which is the better preferred, therefore this proposal is rejected, and it is again the case that B3 is free, right? So B3 goes in its preference list and checks A1, and then it applies to A4. There is again a conflict, and A4 looks at its preference list. It is between B2 and B3, and B3 wins, therefore this is rejected. B2 is now free, so B2 goes ahead in its preference list and it proposes to A3. At this place, A3 is currently unassigned or unmatched, therefore it accepts the proposal and the algorithm terminates, because every B is now matched, right? So now let's see what matching did we get when we executed this algorithm. So just to make the contrast, we will write it in terms of A's. So A1 is assigned B4, A2 is assigned B1, A3 is assigned B2, and A4 is assigned B3. This is the matching output by executing the algorithm from the B side, whereas when we executed the algorithm from the A side, we got A1 B4, A2 B3, A3 B2 and A4 B1, right? So these two matchings are indeed different, and when we execute it from the A side we get one matching, we execute it from the B side we got another matching. On the other hand, at least in this example we saw that the order of the way the A's propose, or in fact you can try it for B's in this example, will not matter. It will always output this same matching, which is A1 B4, A2 B3, A3 B2 and A4 B1. So we would like to prove these properties in general. So what we would like to show is, that one, the output of the Gale-Shapley algorithm, we will just call it as GS algorithm, is a stable matching. So when I say output of the GS algorithm, it could be the output when it is run from the A side as proposing or the B side, and we would like to show that the order in which these A's propose doesn't matter, and it will always output the same matching, which has a very special name, and we will say why that special name is given. So let's again stare at these two matchings. So this was when the B's proposed, so we will call this MB, because the B's had proposed and we got this matching, which is A1 B4 A2 B3. Sorry, maybe this is not the matching, sorry. MB is this, which is A1 B4 A2 B1 A3 B2 and A4 B3. This is the matching when the B side proposed, and so I am removing the proposal sequence because we understand that. And this is the matching when the A side proposed. So we are just calling it MA versus MB. Now let's stare at these two matchings and ask how do these A's fare when these two matchings are with respect to these two matchings. So in fact we have verified that these two are stable for this instance. We would like to prove a general statement that for any instance of the stable matching problem, this algorithm run either from the A side or from the B side will output a stable matching. But let's look at these two matchings. So A1 gets the same partner in both of them, The same is true for A3, which gets the same partner. But if you look at A2, it gets a better partner, that is B3, as opposed to B1 when we ran it from the A side, versus a similar thing happens for A4, which gets B1 versus B3, right? So what we can do is, for every man, we can ask, we'll underline the woman in the preference list if that can be assigned to that man in some stable matching of the instance, right? So currently we have two stable matchings of this instance. We will underline that man. So for example, as if you believe me for the moment that these two are the only stable matchings of this instance, there is no other stable matching, then will I ever underline A1, B2, B2? No, because there is no stable matching that assigns A1 to B2, right? Therefore, I will not underline B2 in A1's preference list. On the other hand, B4, yes, because there are in fact these two stable matchings that I will underline. So, I will underline this. B1 I will not underline because I am telling you, and you have to take it from me, that these two are the only stable matchings of this instance. So, believe me for this moment. So, therefore, I will not underline any of these. What about A2, which B's are underlined? B3 as well as B1, because there is some stable matching in which you get B3, in some stable matching you get B1. This underlined things do not form a matching because they are partners in different stable matchings. For A3 you get B2 only underlined, because assuming that these two are the only stable matchings, there is nothing underlined. For A4 we get B1 and B3, right? So if somebody lists out all of these stable matchings, then we have underlined them. But how do we do that? We do not know. But for now we have two stable matchings, and you believe me that this instance has only two stable matchings. Then we have underlined, these are called as stable partners of that man. That is, A1 has only one stable partner, which is B4. A2 has two stable partners, B3 and B1, which it gets in two different stable matchings. So what we would like to show is that not only that the Gale and Shapley algorithm outputs a stable matching, if you look at every man and somebody has underlined all the women that it can get in different stable matchings of this instance, then when the men were proposing, it will get its most preferred stable partner. That is, amongst the underlined B's, it will get the best woman, right? This happens, this is in fact the way we constructed this. It is not surprising, but we would again like to prove this result. That is, the man, so this man optimal, so this is called as therefore this matching, when the stable matching that is obtained from running the Gale and Shapley algorithm, when the A's propose, is called a man optimal or an A optimal stable matching, because all the A's get their best possible stable partner, right? What would you expect for B's? I could do a symmetric procedure for B's. For B1, there are two stable partners, which is A2 and A4. So these underlines I will just remove. So it is so for B1 it is A2 and A4. For B2 it is A3 and A3. So therefore it is only A3. For B3 it is A4 and A2, and for B4 it is A1 alone, right? So therefore, if you look at what happens when it is A proposing, every B got its worst possible stable partner, because you see that B1 in fact got A4, B2 has no choice because it got A3 in all of them. B3 again got A2, which was the worst possible stable partner, and B4 got A1 again because it has no choice. So when you run the algorithm from the A side, you will get an A optimal stable matching, which is optimized for the A side, That is, amongst all your stable partners, you will get the most preferred stable partner. This is what is true in this example, but we would like to show this in general, and it will simultaneously, that assignment will be the worst possible for women. If you flip the matching, that is, if you run the algorithm from the B side, then it will be optimized for the B side, which is also called as women optimal stable matching, and it will be the worst possible stable partners for the men side, right? And in fact, in our tutorial sheet, we will give an instance which has many stable matchings, not only this MA and MB, which are the extremes. There are many stable matchings, and you can verify that there are some matchings which need not even be man optimal stable, neither woman optimal stable. There is something that is in between, right? So each man will have multiple underlines that we have done, unlike here where very few things are underlined, right? So we will give out those examples because it's tedious to do it here, and we would like to prove a little more theorems in the class. Any questions about this part? Yeah, so please feel free to interrupt. So what we will show is that the output of the Gale and Shapley algorithm is a stable matching, and assuming a proposing algorithm is used, or the man proposing algorithm, the GS algo outputs a man optimal stable matching. These are the two things that we will try to prove now. Yeah. Yeah, so what we will show is, irrespective of what order is used, if you cannot switch sides, you have to decide that the A's are going to propose. As long as you use the A proposing algorithm, you will always output a particular matching which is the man optimal stable matching, and this second statement itself will prove that the order of these proposals does not matter. We will take an arbitrary execution sequence which is any sequence, and we will show that it will output a man optimal stable matching, and this is true for any sequence. Therefore, irrespective of the sequence, it is going to output the man optimal stable matching. Right? Yes. Yeah, that's what I said. No, this is not true. We'll show you an example in which there are multiple stable matchings, and there is a man optimal stable matching, there is a woman optimal stable matching, and there are many other stable matchings which are neither man optimal nor woman optimal, but they are indeed stable. Yes. Very nice. So yeah, so we'll get only two stable matchings by this. If I have time, I will try to show you how to get at least lead you to how to get one from the other. If not, we will set up some questions which will answer this. It's a very nice question, that how do you generate the other stable matchings? Yeah. Okay. Any other questions? Okay. So let's start with one, that is, the output of the Gale and Shapley algorithm is a stable matching. So we want to prove this statement not on an example, but in general. When we are given n men, n women with their preferences, we run the Gale and Shapley algorithm. We know that it terminates. It terminates in a matching because of the way the algorithm is written down. Will it always output a stable matching? That is the question. So what is the line of attack for a proof like this? How do you prove such a statement? Yeah, please think about it for a minute and then suggest some way in which you can try to prove this. Please raise your hand so that. Okay. So it is unstable, right? So let us say that our algorithm has executed and output a matching, which is this matching, and I'm just showing these horizontal edges, but they are just rearranged so that they are horizontal. It doesn't mean that AI is matched to BI. So again, these are the matching edges, and for the sake of contradiction, assume that this is not stable. Therefore, there must exist an AI BJ which forms a blocking pair, and this is not an edge in the matching. Otherwise, it doesn't qualify to be a blocking pair, right? So let's assume that AI BJ blocks M. This is M and AI BJ blocks M. Yeah, how do you proceed? So we will assume for the moment that A's have been proposing, because there are only two ways in which we can output currently matchings. One, either the A's propose or the B's propose, and the order doesn't matter for us. So now you would like to complete this argument and say that either this doesn't happen or we'll see. Yeah, so you have suggested that AI BJ is a blocking pair. What do we do further? You want to show that this is a stable matching, but assume for the sake of contradiction AI BJ blocks M. Then why can't this happen? That is what we have to show, right? Okay. So let's assume for the sake of this proof that the A proposing algorithm was executed, right? Okay. So what went wrong? If the A proposing algorithm was executed, the man AI must have gone in its preference order from the left to right. So in particular, if this is BJ and this is BK, then there were some women ahead, but BJ was before BK. There may be again people in between. Note that this is not a 4x4 system, so there can be many things, but BJ is better preferred than BK. So AI must have proposed to BJ. Remember that everybody whom he has not yet proposed to, it is going to propose. So AI proposed to BJ. So what happened? The algorithm executed in this way. So if it proposed to BJ, then why did it not get accepted? Yeah. Yeah. So this is the output of the matching, but output of the algorithm. But at that point, BJ may have been matched to some other person, because remember the partners keep changing. So BJ may have been matched to somebody else tentatively at that point. I'll just use this tentatively. This was some AK. Now, if BJ rejected AI at that point, AK must be better preferred than AI in BJ's preference list. Only then it will reject it, otherwise it would have accepted the proposal, right? And if at that point BJ has been assigned to AK, what can happen later in the course of the algorithm? So at some point, let's say a woman B gets assigned to BJ gets assigned to her partner AK, gets her partner AK. Then in future, what can be her partners? Can her partners be lower than AK or better than AK? Only better than AK, because she will never accept anything better. So even if the final partner is not AK, it is even better than AK. In which case, BJ is never going to say that I have incentives to move. So if she has rejected AI at certain point, then it must be the case that at that point she was assigned to a better partner, tentatively assigned, and in future her partners can only improve, right? So we make one more observation about this algorithm, that as the algorithm proceeds, a woman which is matched, once she gets matched, that is the B that gets matched, will never become unmatched, because she will either retain that partner or get matched to a better partner, and A can toggle from being matched to being unmatched, because it can get rejected, but B's will, once they get matched, they will keep getting better and better partners, and once she gets a partner, after that she'll only accept better and better partners, so her partners will only improve, right? So only using these two facts, that is AI has proposed to BJ at some point because the algorithm went from the left to right in the preference list of AI, and if BJ rejected it, it must be for somebody who is better than AI, and the final partner of BJ must be a better partner than even AQ, or it could be AQ. Therefore, the output must be a stable matching. And we have just assumed this from the A side. We could have done this from the B side symmetrically to show that the output of the Gale-Shapley when executed, Gale-Shapley algorithm when executed from the B side also outputs a stable matching. Right? But we have not said anything about the optimality from the men side or the women side yet. Is this proof clear? It's a simple proof by contradiction. Okay, so what we know is that the output of the Gale-Shapley algorithm is a stable matching. Now, we should also observe the following, that we never assumed anything about the preference list of the men and the women. They should have a particular form for the instance to admit a stable matching. So, if you give me a set of n men and n women who have complete preferences, that is, as an underlying complete bipartite graph, and you run the Gale-Shapley algorithm, we know that it terminates, it always outputs a matching, and it also outputs a stable matching, which also gives us the answer that every instance of the stable matching problem admits a stable matching, which can be found in linear time by executing the Gale-Shapley algorithm. It can output it may output a unique stable matching. We have not shown such an instance. In fact, there are examples where there can be a unique stable matching. We have seen that there are instances where there are multiple or two stable matchings, and what I have said is that there can be even more stable matchings. So what we have shown is that every instance admits a stable matching. It would be good to construct an example where there is a unique stable matching. And then there are examples where multiple stable matchings, that is greater than 2, exist. SMs is stable matchings exist. So we have only shown this part. This will give as an example, will give as a tutorial question. We will also give an example in the tutorial which will have multiple stable matchings, more than 2 stable matchings, right? Okay, any other questions? Okay, so now we will go to the second part of the thing, that is, we want to show that the order of proposals does not matter, or indeed when we run the Gale-Shapley algorithm, we get a particular matching that is called as the man-optimal stable matching. So somebody has just marked for every man, underlined those women that he can get in some stable matching of the instance, but he has never given you any stable matching. Then what we say is, just pick for each AI its top underlined woman. If you do that, that will be a matching, and that will also be a stable matching, right? So these are very surprising things, that it should be a matching, that it should never happen that 2 AIs get assigned to the same B, and it is also a stable matching. This is what we will show, right? Okay. So we will again proceed for this proof with a contradiction. So we now know that whether it is a what is the quality of that stable matching, we do not know, but it is certainly a stable matching. So we know that the Gale and Shapley algorithm does guarantee a stable matching. Maybe the only contradiction is that it may not output a man-optimal stable matching. So what does this mean? That is, if you look at a particular man AI, it got its partner some BJ. This certainly should have been an underlined woman in its preference list, because the Gale and Shapley outputs a stable matching, therefore it should be an underlined woman. So let's say our algorithm outputs AI BJ as a pair, but if this is the witness man for the contradiction, then where should be its first underlined woman? Where should its first underlined woman lie in its preference list? There are only two things, either before or after. Before, right? Because if this is a man who is a witness for this, that it is a contradiction to the fact that it is man optimal stable. If everybody gets its man optimal stable matching, we are done. That is the first underlined woman. We are done. We don't have anything to show, right? We know that our algorithm outputs a matching which is stable. So we will say that there is a BK which is also an underlined woman. Maybe there are things in between, but this is the first such thing, right? So our algorithm did not output that. Is this clear? So we will look at it in the bipartite setting. So this is the output of the man proposing algorithm, which is MA. So MA edges are of this form, right? And we gave BJ to it in our output, right? But let's assume that, so I'll use another color and use this yellow color. So this is BK, and BK is also a stable partner for AI, but it is in some other stable matching, right? So MA is our output, but there must exist some other stable matching in which AI is matched to BK. Otherwise, by our definition, BK cannot be underlined, right? So therefore, let's call that matching as M, and AI BK belongs to M, right? So that M some matching which matches AI to a better partner is called as M. This is the yellow matching, right? So let's go back and ask what happened when our algorithm was executing. Since this is a better partner for AI must have proposed to BK, right? Okay, and now what we are assuming, here is the place where we will assume that this is some arbitrary execution of the algorithm. So what do I mean by arbitrary? That I have not specified in which order do the men propose. If there is an unmatched man, pick any unmatched man that you like and let him propose to the most preferred woman on his preference list, right? So I don't tell you which order you follow your favorite order. So, but you anyway, there will be a trace of that execution, right? And what we will assume is that during this trace of the execution, there are several rejections that are happening, right? There are some rejections which are happening, and because this algorithm does, for the sake of contradiction, we have said that this does not output a man optimal stable matching. Therefore, there is at least one man AI who is not assigned to its man optimal stable partner BK. There may be multiple such men who are not assigned to their man optimal stable partner, but we'll call this AI BK and a stable pair rejection, right? Remember that our algorithm must have rejected this, BK must have rejected this proposal from AI, otherwise AI would have been matched to BK till the end. So at some point AI rejected BK. So our trace, that is the execution, goes as we were writing first proposal, second proposal, third proposal. Some of them get accepted, some get rejected, and so on, right? So while we do not worry about all rejections, we worry about a rejection which was this underlined rejection, that is a rejection of a stable partner, right? So the rejection of this man-optimal stable partner, which must have happened. At least one is there, there could be multiple. Is everybody with me? So this algorithm is executing, and there is this yellow edge which was rejected by our algorithm, right? And if you look at the trace of the execution of the algorithm, this is the first such yellow rejection. Maybe this execution has rejected many such yellow edges, but there must be a first such rejection. So we will hinge our argument on this first rejection, yellow rejection that has happened. There are some other valid rejections which are not even stable partners. What does it mean? This was not an underlined partner in that A's preferences, right? So there are two things that I have assumed. One is that this is an arbitrary execution of the algorithm, and then whatever is this rejection, this is the first such rejection. So if I go before in the timeline, there is no such yellow rejection that has happened. There are these rejections which are okay. They were not even stable partners, right? So this is the first stable partner rejection. So why did BK reject during our course of algorithm for running of the algorithm this man AI? Yeah. Could it have been free? Then it would not reject. So it must be assigned to an even better person, maybe tentatively, for whom it rejected, right? Okay, so call that man AJ. So it was tentatively assigned to AJ.